This video is about lattice energy and how it applies in ionic compounds. I know that the top says section 8.5. That was from our old book. This is actually in chapter 9 of our current book. Uh, Lattice energy has ramifications for many things. It is very similar in what we just did with PES, photoelectron spectroscopy, in that Coulomb's law is applied. Bigger charges means bigger force, smaller distance means bigger force. Very similar to the idea there. So we'll use Coulomb's law for this idea also. What makes it important is that ionic compound with higher crystal or lattice energy means it has stronger bonds. And those stronger ionic bonds lead to a couple things: higher melting points, boiling points if you got it into liquid form, but also solubility. We talked about neg, sag, and what things dissolve in water, what ionic compounds dissolve in water and which ones don't. The majority of the ones that don't are because their lattice energy are large and those bonds cannot be broken in water. So let's go ahead and get started on this. You can see what you have for a blank. I've made all those bold. So first of all, talking about electrostatic attraction. They are non-directional, which just means that really there's cations. If you think about a ionic compound like is shown here, those cations, like sodium, for instance, is surrounded in all directions by negative ions, and the negative ions are surrounded in all directions by positive ions. There's no actual molecule. There's not an Na and Cl that belong together. It's just ions surrounded by other ions. The chemical formula is just the lowest ratio of those charges, as long as they're balanced and it's neutral, and we have the lowest ratio of positive and negative ions when we write them. The stability of an ionic compound is coming from that formation of that what's called a crystal lattice. That's why it's called lattice energy. There's always energy released when that crystal forms from the gas state. Ions in the gas state. And I'm guessing what you're thinking is, well, sodium isn't an ion in the gas state. Correct. But if you made sodium an ion in the gas state and chlorine an ion in the gas state, when they came together, that's what's called lattice energy. It always gives off energy, sometimes more than others. But it's always exothermic. And as I talked about a little bit with Coulomb's law already, the size of that, as you see down here, depends directly on the size of the charges of those ions and inversely on the distance. So we'll address both of those here as we go through this. So this is very similar to the equation we saw with Coulomb's law when we talked about PES. So when those gaseous ions pack together, that's what lattice energy. So why do we care? We're not going to use this equation and actually calculate anything. But when we look at the charges and the distances, we need to be able to apply those ideas without actually using the formula. So Q1 and Q2 are the charges on ions. If we're talking about, say, sodium chloride, it'd be +1, -1. And then the distance between the cations and anions would be what we're looking at for R there. So if we want to compare some things, which you'll definitely be practicing on in a little bit, if we want to compare some compounds as far as, let's say, what would probably have the highest melting point, which means it has the strongest lattice energy, NaF or NaCl. If you look at something like that, both those compounds have a +1 and -1 charge on their ions. So that means that will not be the big factor, but the distance is going to be a larger factor. Both of them have sodium compounds, but here, NaF, fluoride is a smaller ion than chloride. Therefore, these guys can get closer together. Since those ions can get closer together, they will have a larger lattice energy, and the melting point of NaF I would expect to be larger than NaCl. I don't know what they are offhand, but we're just going to make some generalizations based on charges and distances. So that's if the charges were the same. So now let's say that we have very similar things, but we have Kf and K2O. So in that case, we have +1 -1 for Kf. Fluorine and oxygen are really close to one another on a periodic table. But if we talk about potassium and oxygen, that's +1 and -2. Charges trump the distance. If the charges are the same, then you want to look at distance and see how close. The ones that can get closer together would be the highest lattice energy, which means it is going to be the highest melting point as a solid, which means it's going to be less likely to dissolve in water the stronger the lattice energy is. In this case, if I want to compare these two, it's like, oh, they both have potassium, which are +1s. So what does the anion have effect on? Well, now instead of +1 -1, it's going to be +1 -2, which effectively doubles the lattice energy once we have a bigger charge on top. Even if the distance is much bigger or it is different, it's not going to be different enough to make the lattice energy change that much. That charge difference, it definitely trumps. So when we think about some things that don't dissolve in water, let's just say, I don't know, aluminum phosphate. That doesn't dissolve in water. Think about the size of those charges. +3, -3. That is 3 times 3, 9. 9 times just the top of that is going to be 9 times stronger than something like NaCl. Not taking into account the distances between them yet, which is also a factor, but this is a huge factor, the size of those charges, as far as the strength of those forces, bonds that are holding them together. So how to determine lattice energy. We can think about this being strength of the forces, but where that comes from can be tricky to get. So here's an example of how I do it with the Bohr-Haber process. Hypothetical series of reactions that represents the formation of a compound from its elements. Reaction shows that the change in enthalpy for each reaction is known except for just the lattice energy at the end. So what the heck does that mean? Let's walk through this real quick. So for instance, say I'm going from, let's just keep it simple again, with Na solid and chloride gas, and we're trying to get to NaCl. Some things need to happen to make that happen. For instance, the sodium would need to turn to a gas. That's this process here, the sublimation. And that's endothermic. That takes energy to make that happen. And we'll see this on a chart in a little bit. The chart's not super easy to see on your sheet, but I'll show it on here and hopefully make more sense. Now we take this gas and we're going to remove an electron from it to make it a sodium ion. Because remember, lattice energy is the energy that is released when the ions are joining together in a gaseous form. So we're just kind of going through the steps that have to occur in figuring out how lattice energy can be determined. So in the case of sodium, it would just be 1 electron. If in the case of, say, magnesium, there'd be 2 electrons, so there'd be even more energy needed to go in that process to make it up Mg2+. Now, if we think about the non-metal, in this case, the chlorine, chlorine would have a bond to itself like this. We'd have to break that bond. That's going to take some energy, endothermic. So energy in, energy in, energy in so far to make this happen. We already talked about how lattice energy is going to release energy, but we're going to see how all these work together. Then we have something again, let's say it's chlorine. You add an electron to it. Well, that's a stable situation. It wants that electron. That's exothermic. It's going to release some energy in that process. And now here's that the actual lattice energy. This is called lattice energy here. This right here. Gaseous metal ion, gaseous non-metal ion getting together to make a solid ionic compound. That's called lattice energy. That's what's going to, the strength of that or the size of that is what's going to determine a lot of properties that, as we've been talking about here. So let's kind of look at this on a chart. This is tough to see. So I'm going to try to show you as best I can what we're talking about here. This is actually looking at MgO, where we have, this is the lattice energy that's released, and that just means higher to lower. So the energy that's released when Mg ions, 2 plus ions, and O minus 2 ions get together. The other part of this process is showing what I just talked about, how the amount of energy going in to break apart the magnesium, make magnesium a solid to a gas, and all those other steps. I'm going to show you the next one. Hopefully will show up a little bit better for you, which is out of your book. So you can see this in chapter 9. And this is talking specifically about sodium chloride. So here is where it starts as sodium and chloride in its standard states. And it just shows how the energy is absorbed each time. So here's the energy absorbed, heat of vaporization to go from the solid to the gas. Energy is absorbed. In this next step, going from, what are we doing here? The next step is going from the Cl2 to Cl onlys. The next step here is to ionize the sodium. So it's slightly out of order before. The next step is to release that energy as you give an electron to the chlorine. And now you have them as their ions. And then this release, those ions getting together, that is called lattice energy right here. So this value here ends up being the overall enthalpy change for sodium as a solid getting together with chloride gas in the standard state. There's a bunch of energy in, here's a little bit of energy out, here's more energy out. So this ends up being the enthalpy change for that whole process, but this here is called the lattice energy, as far as that combination of ions getting together. And if we think about that lattice energy, that will allow us to, if we look at those charges and a distance between charges, allow us to compare a lot of ionic compounds in terms of their strength of those forces because of those charges, which will lead to, again, solubility and melting point and things like that. That is all about lattice energy.